The final technique I want to go over is structural equation modeling, and this is another one which the goal here is less about giving you information about how to run one, or at least a starting off point to learning to run one, and more of a general understanding of what's being communicated when you read an article that uses structural equation modeling. And again, I do not want to come across as an elitist. I just really believe that I want to define each one of these of what I'm expecting to learn from it. Structural equation modeling, actually, I know people that they specifically have advanced degrees simply in this technique. There's a lot of things going on with structural equation modeling. There's a lot of both methodological and statistical techniques that are involved. For example, if you're running a structural equation modeling, you're not running it in SPSS. Generally speaking, you're buying a program that is all it is designed to do. And there are specific statistical packages out there that are dedicated just to running various types of structural equation modeling. So this is a very big, broad overview, and mainly being provided to give you kind of an idea of what to be looking for, again, when you're reading an article that uses structural equation modeling and have an idea of what they're trying to do. So generally speaking, a structural equation model is combining elements of multiple regression with factor analysis and PCA into one gigantic model. And generally speaking, if you think about this, if we truly were talking about an overall model, so in other words, we're not including, so think about it this way. If you have a 5-item measure of extroversion, before you ever put that into a multiple regression, you're going to do a separate set of analyses to see if it's highly internally consistent, and then you're going to take that final variable that you create from those 5 items, assuming it is consistent, and use that in the multiple regression. And you're only necessarily going to be looking at interconnections between that particular variable and variables that you're interested in looking for that relationship for. A structural equation model at its basic level is actually looking at every single item interrelated with every other single item in your study. So it's looking for latent variables, factors, or constructs, not based on previous research, but based on the data. So for instance, if you had that 5-item extroversion scale in a structural equation model, the structural equation model is actually going to ask the question, is each one of those items related to other factors or other variables in your model? Are they related to each other? Are they a latent variable? In other words, are they so related that we can assume that they're in one factor or they represent one construct? And how do they interrelate? So effectively, this is kind of like factor analysis and multiple regression, both of them on acid, just going wild. Now, because of that, that means that most structural equation models, to begin with, are poor-fitting models because they have too many intercorrelations. They're looking at everything. And that's where the methodology component comes in. We need to actually go in and determine whether or not we actually want the structural equation model, that is, to statistically be looking at various connections. So when we're looking at a structural equation model, the first thing we want to look at is the actual model itself, the physical visual model that's presented in an SEM article. And what you're looking for are circles or ovals. Those ovals represent latent variables, either latent variables that have been identified statistically or the latent variables the structural equation model was told to look for. So these are clusters of individual items that are lumping together to basically measure a single psychological factor or construct. Anytime we see squares, we're looking at single observed variables, measures, indicators, manifest variables. So if we have a variable that is its own construct but is only measured with a single variable, it's going to be represented by a square in that model. If we have a latent variable that has 5 individual or manifest variables that make up that latent variable, we're actually going to see that oval connected to 5 squares. The next thing we're going to see in the model are arrows, and we can see direction of influence. So we'll see some arrows that basically are unidirectional. They're suggesting, for instance, that the variance should only be looked at one way. So for instance, again, if I have 5 latent variables, 5 manifest variables, I should say, 5 squares that are all being expected to represent a single latent variable, an oval, I would have unidirectional arrows from the box to that arrow. indicating their variance is explaining that latent variable and nothing else. We can also have associations not explained within the model, and those are simply not visualized, or they can be visualized with multi-arrow or multi-dimensional arrows going both ways. That means the variance is allowed. Now again, when you first look at a structural equation model, the first thing that you want to ask is, what did they leave out? What connections did they not look at? Because that means they made some methodological choices in what to examine. So here's a very simple structural equation model. We have three variables which are related to family support. So family support itself is represented by self-rating closeness, spousal rating, and kids rating. So there's three variables that are going into family support. And each one of those variables, by the way, has error variance associated with it. Then we have depression, and depression is measured through three different measures of depression, each with error, and we have physical health. And what we're expecting in this particular structural equation model is that family support, as measured by three variables, is related to depression and physical health, but depression and physical health are not related to each other. So like I said, you want to ask about what arrows are missing from this. Which arrows are unidirectional? Could depression result in poorer family support? Possibly, but that's not being looked at in this model. So as you get more depressed, would it be harder for you to get family support? If you believe that, you'd want an arrow going both ways between those two constructs. Again, this particular model expects that there is no relationship, nor does it look for a relationship between depression and physical health. So when you're looking at a structural equation model, you'll often find result sections that goes on for pages and pages and pages. What I'm telling you to do is, before you ever look at those results, really look at the visual representation of the model and ask yourself, do you agree with the model they're suggesting? Because a structural equation model at its base level initially will run an analysis looking at all possible interconnections. So every possible line you could draw would be there. But that's far too confusing and would overfit the model. What we're then looking for is, what was the best fitting model that actually made theoretical sense? So that's some subjective choices. Now those choices hopefully would be made on literature review and past research. So for example, if you find that most research suggests that depression does not influence family support, well, that justifies only looking for that unidirectional arrow. If you found research that suggests that depression and physical health are rarely related, that would again support not looking for that relationship. But again, when you're reading a structural equation model article, one of the first things you really want to spend some time on is really look at their model. What are they doing? What are the directions of those arrows? What arrows are missing? And do you agree with that model based on your understanding of the constructs that they're examining? And again, we may change the model. And a lot of times when you're looking at structural equation modeling, they'll show the initial suggested model, and then they may show an adjusted model based on the data. So for instance, they may have made the argument that depression and physical health should not be related, but when they ran the model, they found it was poorly fitting unless they included that relationship between depression and physical health, which made the model a better fit for the data. And again, we're asking, is this model a significant representation of how this variance is actually being partialed? So what are structural equation models? What can you do with these models? You can look for latent and observed variables. So basically, built into this system is factor analysis, or PCA. You can also look to see if multiple indicators of the same concept are truly related to one latent construct, or they are interrelated with other constructs. We can actually get measurement error and the differences in measurement error in each of the latent variables. And we can also look at restrictions on the model parameters and the tests of model fit. So restrictions on model parameters are, we can actually let data decide what scenarios or what particular variance combinations we don't want to look at. So for instance, we may have a model which actually is overfitting, and we recognize that multiple of those connections are not significant or are very weak. We can then remove them from additional models. And as we go through that process, we then test each model to see, is it a better or worse fit than the previous one? So again, kind of looking at multiple regression, we often talked about with a hierarchical multiple regression, one of the things we're wanting to do is look at model fit and find the best fitting model. The same thing is occurring at structural equation modeling. SEM is also asking, how do various models compare to each other? However, it's much more complex, as usually with structural equation models, we'll have a lot of variables involved, and each variable in the model itself includes the actual individual variables, the PCAs and the factor analyses that make up those observed variables. So, what are structural equation models? What can't you do? You can't prove causation, and you can't prove that a model is correct. Basically, every time you run a structural equation model, you are making choices. You are basically looking at an enormous number of correlations and intercorrelations and intracorrelations. And therefore, you can look for themes, you can look for patterns. You really can't get to causation with a structural equation model. The old equation, the old saying of correlation does not equal causation should probably also be structural equation models do not equal causation. The only way that they could actually equate to a causation is if you actually have accounted for causation in every possible combination of those arrows that you put in that model. So do you have temporal precedence with every model? Have you ruled out every possible cause? And for the most part, structural equation models are usually used in very kind of messy applied situations to look for larger theoretical models that are very complex explaining what's going on. You also can't prove a model is correct. You can simply prove that it's a fairly good fit for the data that you have. So generally speaking, you have a space with all models. Then you have a smaller space with models that are consistent with the data. And then you have the smaller still, the models that are consistent with the data and consistent with reality. So basically, the all models is if you took your entire data set and just ran an unspecified structural equation model. You let it look for every possible variance, every possible connection, and basically account for all variance. That would be an all model, and it would be fairly useless because it would just tell you everything's somewhat intercorrelated or not intercorrelated. You would then ask it for what's a best fitting model that actually makes some kind of sense. That's a model consistent with the data. And finally, you would ask, is that model then consistent with previous findings, literature reviews, meta-analyses, and theory? That would be that model consistent with reality and the data. So again, you really get down to the idea of latent variables. They're the variables of interest, but they're not directly measured. And one of the advantages of structural equation modeling is that it actually identifies and labels latent variables as such. In most psychology research, we usually talk about latent variables as if they are known. That they are directly measured. Usually when we're talking about, for example, self-esteem, we'll discuss how we measured it, how we quantified it, but at the end of the day, it's a single measurement in an analysis. One of the reasons people like structural equation modeling is they visually remind us that they are simply latent variables. They're not directly measured. They're being inferred from a set of individual predictors. So common latent variables include intelligence, trust, democracy, disease, disturbance variables, basically almost anything that has to do with human behavior, attitudes, feelings, emotions, etc. What we're interested in psychology. The other thing we have to ask is the model recursive or non-recursive? So a recursive model means the direction of influence is determined. There's no reciprocal causation. There is no feedback loops. Disturbances are not correlated. So disturbances basically mean error. We're not allowing error to be interrelated to each other. We're not looking for error to be correlated with other error for latent variables. And we're also dictating the direction of the influence based hopefully on past theory. A non-recursive model allows reciprocal causation. It allows those double-angled arrows. It allows feedback loops, and it expects the error to possibly be correlated. Now, the difference between the two of these is a non-recursive model tends to be better fitting to the data, but possibly less generalizable. A recursive model is often not quite as good a fit to the data, but if built on theory and past research is maybe more generalizable. And this is another thing you want to ask. When you're looking at a structural equation model, you want to both visually determine, is it a recursive or a non-recursive model? And you also want to know that as you're moving forward, because it's generally two different purposes. A recursive model is generally going to be a very theory-driven model. A non-recursive model is usually going to be a more data-driven model. So how do you actually do structural equation modeling? Well, there's 6 steps. The first one is to specification. You want to specify what are the actual observed variables. So every single variable that's measured is going to be a part of the structural equation model. What are those variables? Then you're going to basically determine what are the expected latent variables. So which particular individual measures or variables are you expecting to cluster together into latent variables? What are the expected relationships between those latent variables, and what are the relationship between the latent variables and the observed variables? So again, the boxes and the circles. You want to then have an implied covariation matrix. You're going to look at that to see if you're getting basically just correlations that support your initial hypotheses and specification. And then based on your actual first model, your structural equation model, you're going to try to determine if that model is under-identified, just identified, or over-identified. Over-identified means that, yes, you've got a good fitting model, but it's so complex now that it's basically data-driven and not theory-driven. Under-identified means that it's a very clear model, but it's ignoring significant relationships that you've told the model not to look at that probably need to be included. And just identified is kind of a magic subjective sweet spot where the model makes sense, it's supported by past theory, and it's explaining enough of the variance for you to trust those findings. And a lot of the statistical analysis in structural equation modeling really comes down to that estimation of identification, measures of model fit, and if the model is not fitting well, respecification, and then comparing the respecified model to the original model, again looking for a significant improvement in fit. So model fit, there's a lot of different ways to look at model fit, and again, this is an entire area of statistical knowledge that I've put down to one slide. So basically, there's component fit, subjective, substantive experience. Are the signs correct? Are there any nonsensical results? Are the R-squares where you'd expect them? Is there negative error variance? Are the standard errors seeming reasonable? So this is basically just kind of subjective process of looking at just the correlations that you're finding within the structural equation modeling. If you're expecting two latent variables to be highly positively correlated, are there? Are there any nonsensical results? Are there any variables that basically you would never expect to be related that suddenly are? What are the effect sizes for the individual equations? And are they effect sizes that you'd expect to find? Is there negative error variances? Are there some variables that actually have negative error? So if that's usually an example of an overfitting model, because that means that in an effort to assign all variance, all variables should have some positive error. All variables have error in them. If there's a variable with negative error, that means a problem. And also the standard error within each variable. Does that seem reasonable? Is the distributions making sense? Beyond that, we can actually look for test statistics. So one of the test statistics we can look at is simply a chi-square difference between the various models. This works best if we have statistical power of at least 75 people or more. There's many other goodness of fit statistics. There's the normed fit index. We usually want to see that at 0.9 or 0.95 or higher. Now it does inflate with more complex models. So the more complex the model, the higher it's going to be. But again, if you're reading a structural equation model, what you're looking for is a significant chi-square if they present it, as long as they have an N of 75 or greater. You're also looking for an NFI of honestly 0.95 or higher. You're also looking, if they present it, for an AIC smaller than better. And this is usually used for comparison of models. So if they're comparing multiple models, you're wanting to look at the AIC, and you want to make sure that the models that they're using are smaller than the models they're discarding. Probably the most common measure for this is the RMSEA, or the root mean square error of approximation. And again, we're wanting to see this number small. So generally speaking, when you read a structural equation modeling, they're probably going to present all of this data. And rarely have I read a structural equation model that makes a strong argument with every single point. So again, grain of salt. If you've got a significant chi-square, your root mean squared error of approximation is 0.05. You've got a low AIC, but the NFI is 0.87. That doesn't mean it's a bad model, but it also means it's not a great model. There's something else in there. There's some data that wasn't necessarily explained. The more of these that are positive, the more of these that are effective, the more of these that are in this realm, if you will. So significant chi-square, NFI of 0.95 or higher, very small AIC of the final model, and an RMSEA of 0.05 or less, the more you can trust that that structural equation modeling is at least capturing a significant way to think about the model based on the data. So for example, this is a very simple structural equation model. It is simply looking at the error for each predictor, 5 predictors, and how those predictors are predicting one latent variable. So this is about as simple a model of a structural equation model as you can. And we have a chi-square that is significant. We have an IFI rating of 0.87. We have an RMSA of 0.25 with an N of 801. So what this tells us is this is not particularly a great model at this point. The RMSEA is not 0.05. The FI factor is below 0.95. So what this is telling us is there's interrelationships here that are not being captured by this model. Now we may want to re-specify, and as we reclassify at this point, we may change some of those relationships, we may drop a particular variable, and we may find an increase to where now, for instance, the chi-square is not significant, the RFI is actually 1.0, and the RMSEA is 0.03. And again, we have our N. So each time we re-specify, we're going to be changing various things, and it's rare that we're going to get everything actually aligned to where all indicators of a good fitting model all agree. And again, what we did to get this change is we simply allowed some of the variance of the 2 variables, boycotts and petitions, to be included in the model. And as we add more models, as we add more particular paths, we may be getting to a better fitting re-specified model.